All right, so why don't we get started? Getting a little bit of feedback on the mic. Hopefully that won't be an issue today. You can hear that hum? I'm sure that's right. If you have any suggestions on getting rid of the hum, let me know. So today we're going to talk about cache memories, their organization, and their performance. First, we're going to review a couple things from the last class. The first thing is this notion of locality. It says that programs tend to access data and access code that's either the same or close by to things they've used recently. We distinguish between two types of locality. Temporal locality, which is where the actual location is accessed again in the near future, versus spatial locality, where it's not necessarily the exact same location, but it's a nearby one. So it might be, for instance, in the same cache line. And we have this picture of the memory hierarchy. And I want to stress that this is obviously not drawn to scale, right? I mean, it wouldn't be a nice, smooth thing like this. It would be sort of exponentially shooting out wide thing towards the bottom. But this gives the idea that at the top, we have these smaller, faster, but more expensive per byte storage devices. And as we get increasingly towards the bottom, the storage devices get larger, slower, but cheaper per byte. And data gets moved between consecutive layers, generally. Okay, and then we have this notion of that we can view any two layers, consecutive layers in this hierarchy, as one being the cache for the layer right below it. And so, if here's the cache, again, this is much smaller size than the thing below it. Let's call the thing below it memory. We think of memory is being divided into blocks that are the size of the unit of transfer back and forth. Okay, so what can happen here is that if you want to access this block from memory, you bring it into the cache itself. Okay, and all this is saying about this partitioning is really an alignment issue, right? That basically, although this cache line here, say, could hold a certain amount of data no matter where it resided in memory. So for instance, it might hold like data that look like that, right? That's not the way the machines work. For simplicity in doing address calculation and data movement and so forth, you move data between levels on alignment boundaries, okay? Good, similarly for 10. Okay, so we have this notion of a hit, which is when you go to access something that's already in the cache, so that's good. And then a miss is when it's not there. And you have to go fetch it from the next level down in the hierarchy, or if it's not there, then recursively you continue on down the hierarchy. You find it, and you fetch it and stick it in the cache. Okay? And when you do that, you have two choices. One is, where do you want to place the new data? And a related choice is, what do you want to evict? Okay, so that is the difference between the placement policy and the replacement policy. Okay, what do you want to evict or replace? What is the victim? And we mentioned there were three types of cache misses: cold, capacity, and conflict. Cold, if you recall, is because sort of the cache starts empty, and if you ever access something for the first time, there's no way it can be in your cache. So that's there's no way of getting around that miss. It's a cold or compulsory miss. Any system must pay that kind of miss. Capacity miss has to do with the size of the cache. So if the cache relative to the active working set of the program, the set of data the program is touching, is if the cache is smaller, then you start getting misses because you're evicting things from the cache that you need later. Okay. And finally, when you place data, you don't have complete freedom in wherever to place it in the cache, but there's some restrictions on where in the cache it goes, then you can have what's known as conflict misses, where data items that sort of collide in where they want to be placed causes them to evict one another, even if there's plenty of space elsewhere in the cache. Yes?
Why not initialize the system so a total miss of application? Why would
That is fine, but it doesn't get beyond the notion. So that would save the lookup in the cache, but you still have to pay the cost of fetching the data. Yeah. And so from the viewpoint of the program that's running, you're still having to pay the latency to go get it from something other than the cache, right? The memory is not the cache. Okay? Yes?
For completeness, why we don't just keep like a list of empty slots, then we allocate based on the empty slots? Why we would have to like...
Yes, in fact, that's a good strategy that gets used, for instance, in memory allocators. When you write your malloc lab, you do your malloc lab, you will explore different ways of keeping track of everywhere in the cache that there's holes, there's available slots. The challenge here is that these things have to run really fast. And so we don't want to pay the extra cycles to do some fancy lookup to find where things are. Okay, so they're kept very simple, and it's similar to, we'll see later that the actual mapping of the placement algorithms are very straightforward. They're just extracting bits off of the address that you're actually using. So it's just a masking of the bits or a selecting of those bits, which is very fast, as opposed to say some complicated scheme where you, I don't know, maybe there's some decision tree to figure out where it belongs, or you take the address and you apply some hash function so that sort of randomize where it fits in the cache, which might make it less likely that you have these bad conflicts and so forth. But the decision was made that was going to add cycles on the latency, and particularly for read misses, the program is often waiting for the data to get back. And so if you can make that run as fast as possible, that's going to be good for the programs. Okay, so you could do it, but it's just higher overhead. But when we get to things like memory allocators, like malloc, those aren't called all that frequently and so forth, then you could do the tricks you mentioned. Good. Okay, so where does it fit in the system? So the cache memories are on chip. There's often multiple levels of them. They can be accessed directly by the registers, and they have, through the bus interface, access to write and read to the memory. We covered that last time. Looking a little bit more closely in terms of the logic within the CPU, we have an extraction cache here, okay, where you're storing recent instructions. So if you have a locality in your instructions, you'll get hits in this cache, and then these instructions get decoded and they get executed. And then if there's a load or a store, then you're going to want to fetch addresses, okay? So for instance, for load, you pass an address, you get back a data value. Store, you pass both the address and the data you want to write. If you get a hit in the cache, then everything stays on chip, at least in the L1 or L2 cache, and so it stays very close to the processor within the core itself. Even an L3 cache is typically on chip, so that's pretty good as well. But if you miss all those, then you usually have to go off chip to DRAM memory somewhere. Okay, so again, that's schematically how it looks like. If you were to, look inside your machines, you might see something that looks like this, right? It's sort of the whole CPU with a cover on it that, branded cover, and all the goodies are inside it. If you look inside it, you see, again, these are not to scale. You'd see something that looks like this after you, either before they put all this encasing around it, or if you dissolved off all the encasing, you'd see something like that. We'll see a close-up of that on the next slide. This whole, so that's within the chip. Then the whole system that includes these buses and so forth and a lot of other things is all part of one motherboard. It looks like that. And then the DRAM is in in these DIMMs that look something like that. Okay. So looking more closely at just one of those CPU chips, you get a picture that looks like this. This happens to be the Sandy Bridge processor die. you can see here that there are, so here's a core right here. Here's another one here. Within the core, you can see the L1 cache is there, L2 cache is there. I mean, not that you can look at it and tell what it is, but if you're used to looking at these things, you know, caches have these very regular structures. There are 8 cores in all, 1, 2, 3, 4, 5, 6, 7, 8. They're all sharing on chip the L3 cache, which is this huge thing here, and it's divided into banks, and here you're showing one bank of L3 cache. Okay, DRAM controller and so forth. Okay, so in this particular die, there's a 32 kilobyte instruction cache, 32 kilobyte data cache, 256 kilobyte L2, which is the backup cache for both the instruction and the data, and then this L3 cache, depending on how much money you spend, can be anywhere from 3 to 20 megabytes. Okay, so any questions on that? Okay, so now I look at a picture like this and I say, you know, does it really look like that? I mean, you know, it's awful colorful, right? Who knows how they get it so colorful? Is it really that colorful?
No, you mean it's I forget exactly, but
It's just a photography trick, right? They shine a halogen, tungsten halogen light on it that has a range of you know, spectrum within it, and depending on what it is, it reflects in different ways, and they get these pretty color pictures. Okay. Otherwise, it's, you know, it's all just whatever, boring black and gray and stuff like that. Okay, but they're all, you know, they're beautiful. It's like the pictures they show you from space, right? You know, okay, space, it's just dark out there, right? And a little bit of light. But when they show you these you know, astronomical phenomenon, they color code it, right? So that everything looks so colorful. Right? All right, same idea, sort of. All right, so let's talk some more about caches. So caches can be organized in various ways. Here we're showing an organized, we're going to define these terms, S, E, B. So S is going to be the number of sets, what we call sets, and E is the number of lines per set. Okay, and they're both powers of 2. And the choices for E and S vary from processor to processor. And basically what happens is that the placement policy will dictate which of these sets a particular cache, particular address, cache block based on its address goes, and then you have a choice within the set as to where to put it. And so you might, for instance, as part of the replacement policy, you might decide to evict the least recently used of the ones in this set. Okay. Now, if you look at one of these lines, it's more than just the data. We're going to let B denote the number of bytes per cache block, so that's the data, and again, that's a power of 2. But there's also this tag and this valid bit. Okay, the valid bit just says that something valid data is stored in there. So initially, that would be set to false. We'll talk about the tag in a second. Okay. So if you look at the address, then as I said, the placement policy and everything is just dictated by the address itself. There's no, you know, separate hash function or any sort of tricky scrambling of the bits or whatever. And it works as follows. So you use these. So there's B bits where B equals 2. So capital B is the amount of data in one of these blocks. So that's going to be used to address where within the block, once we've got it, we want to go. But in order to get there, first we have to pick a set. The set is the next S bits, most significant bits above the B bits. Okay, so if this is, as a bit representation, if that's 0, you'd be up here. If that's all 1s, you'd be down here. Okay, so this example, it must have been all 1s because we're focusing on that set. Okay, and then you Then the rest of the address becomes the tag. Okay, and so if the address is W bits wide, then T plus S plus B equals W. And you use this tag to compare against the tags of things that are stored in this set. And if there's a match and the line is also valid, then you have a hit. Otherwise, it's miss. So if you have a hit that says this is the right data block, and then I use the block offset to say where the data starts. Right? So in this case, it starts at that second byte. Okay, and then where the data ends. Anybody know how you figure that out? Can you go guess? Well, it's encoded in the instruction itself, right? Remember, if it's a move L, it's long. Move Q, it's a quad, whatever. So the instruction itself will indicate the length, the ending address of it. Okay, so an extreme example that's popular for its simplicity, and so on less expensive settings or more power frugal settings, you may see a direct map cache. So that's the case where E equals 1. Okay, so there's exactly one place that every address can go in your cache. And so, as you can imagine, that makes the most likely to suffer from these conflict misses, right? Because there's no choices going on. There's just one place. Okay, so as before, we find the set, but now there's no there's not multiple tags we have to compare against. We just compare against the one tag. And if the tags match and the valid bit is set, then we have a hit. So let's assume that's what happened. Then we use these bits here, which is 4. And so we know we want to start from 4. And that's where the data starts that we're trying to retrieve. Okay. So if, for instance, this was an int, and so we want 4 bytes, then the green bytes would be the ones. Yes?
Can you explain how the validity tag is set? And then, I guess I'm just wondering how we can assume that because it's 1, that this is a case.
So initially, these are all going to be 0, right? Nothing in the cache is valid. Every time you bring something into the cache, you mark the bit as valid. Okay.
What happens if you have like a conflict? Because you only have a bit.
So on conflicts, that you kick out what's there, and you put in the new thing, and so the bit will stay as 1. Okay. And there are other cases in which the valid bits will get reset to 0. For instance, if you swap in a new process, or if there's a if there's like multiple cores and one core sort of steals the cache from another, then you could reset this to 0, even though you didn't have anything to put in it, anything to replace with it right away as well. Okay. The opposite is if either the valid bit is not set or the tag doesn't match. That'll be a miss. And in a direct map cache, there's only you've got to make space for the new thing in here. So you always evict what's there. There's only one choice of what to evict, and you replace it with the new data that you fetch from cache, from memory. Yes.
So what happens if if I want a float, like it wants 8 bytes, like in the last example. So like in this offset, in this set, you only have like the last 4 that you're reading. But what if I want it?
Then you'd have to do 2 cache references.
So I have to read the next.
Yeah, you'd have to read not just this address, but the next one after it.
But what if the other one is invalid?
So the case you don't want is you don't want 2 consecutive cache lines to map to the exact same set. Then you'd be really in trouble. okay? But fortunately, systems are designed to avoid that case, okay? But what you're pointing to is the reason that sort of aligned, why things like structs and things, you want them aligned, right? Because if they're aligned and you have this 8-byte value, then you're guaranteed that it won't span across 2 cache lines, so it'll be much more efficient for the system. Yes?
Oh, so since e equals 1, that means there's 2 lines in this situation?
E equals 1. Oh, that's a good catch. No, sorry. E is the number of lines. Little e is the power of 2. So little e would be 0,
Oh, okay, I see.
and big E is 1. Yeah, good. Yeah, so the notation we're going to use is that the E version is always the big E version is always 2 to the little e version. Similarly for B, capital B we'll say is 2 to the little b, and the capital S is 2 to the little s. So yeah, little e is 0, so big E is 1. Good. All right, so you're going to, writing caches and things like that in your assignments in a couple of your labs. And so, if you're, so these, all this is happening in hardware. But if you want to simulate a cache like we do for your labs, then you want to mimic the behavior in your code. Okay, so let's take the case where the you have 16 bytes, and B is 2, S is 4, and E is 1. Okay, so because of that, because B is 2, then little b is 1. Because S is 4, then little s, 2 to 2, little s is 4. And the other key to note here is, so how big the tag is depends on how large the address is. Okay, so in this toy example where addresses are only 4 bits long, we only have 1 bit left for tag. Okay, just keeps it simple. Otherwise, I mean, if the addresses were 16 bits, we'd have 13 bits left for tag. Okay, so here we have a address sequence, and let's just say we're doing reads, and we're only doing and they're byte reads. And let's suppose that we want to access 0, 1, 7, 8, and 0 again. So when we look at the binary representations for them, they look like this. And then we've color-coded them according to whether they're part of the B, the S, or the T. Right? So in this case, there's just 1 B bit, so that's there. There's 2 S bits because we have these 4 sets. And so it's these S bits that will determine which set in this direct map cache. Okay, so the fact that this is 0, 0 means that the first axis is this set right here. Okay? All right, well, the cache is empty, so clearly it's going to be miss. And then we put it in there. So when we put it in there, we set the valid bit to 1 in our code. The tag now is just the red part. In this case, it's just very simple. It's just the bit 0. And we store the data. Okay. Now the data is the entire cache line, which is 2 bytes. So even though the program only wanted byte 0, byte 1 comes along for the ride. Okay. So now this cache block holds both byte 0 and byte 1. Okay. And in general, it holds the whole cache line's worth of data. No matter which element in the cache line you wanted, it's going to bring in the entire cache line. Okay. So what about this next one? So this next one comes in. Is that going to be a hit or a miss?
Miss.
It's actually going to be a hit, right? Because if you go, because basically it's part of the same cache line, right? Address 1 and address 0 within the same cache line. To look at how it plays out in your simulation, you'd say, okay, this is 0. And so therefore it goes to the same set. I'm looking for a tag as 0, and I found it. Okay, and so it's a hit. And the difference here is that in the first case, once I found that data, or once I put it in the cache, I was interested in the 0th byte, and here I'm interested in the first byte. So they are 2 different locations, but they're within the same cache line. Okay, so that becomes a hit. Oh, got ahead of myself. So the next one, you look in the set 1, 1. There's nothing there, so that's clearly a miss. Okay, so you put it in there, and again, it's it brings in the entire cache block, which is both 6 and 7. You'd only be interested in the first, instead of the 0, the first byte of that, and so you'd want 7. Now what happens when 8 comes in? Yes?
It's a miss because it's full, and it's going to want to put it in set 0, set 0, tag of 1, and store it locked, with 8 in there.
Yes, so exactly. So it's going to come in here, and 0, 0, it's going to evict that guy, and you get the block that's shown. Okay, so now we go back to 0, and we're hopeful since we just accessed 0 only four accesses ago, it would be in the cache, but we've just had a conflict miss, right? Two things that, even though there's plenty of space in the cache, two things that map to the same set, and therefore this also gives this. Okay. So these are all cold misses because they're the first time, compulsory misses because they're the first time we see it. This one is a conflict miss. Any questions on that? Yes?
How do you get the 6 and 7?
So it's, again, the memory is divided into, we think of it as partitioned into blocks of size B. So in this case, there's 2 bytes per block, which means that the first block is 0 and 1, then 2 and 3, 4 and 5, 6 and 7, 8 and 9, and so forth. Okay? So if you address either of those two, in any one of the pair, you get them both in there. Yes?
You said 8 is a cold miss, but didn't we already put something in set 0? So wouldn't that be a conflict or capacity miss?
So that's a good question. One of the ways to think about it is that if the cache were infinitely large, would it still be a miss? And the answer is yes, because we don't have 8 in there at all.
Oh, so that's
Right?
okay. But if you have 8 there, you wouldn't have a miss at all, right? So like you said the reason why it's a cold miss is because 8 is not in there?
Right. Well, it's because the first time you've ever accessed that cache line.
Oh, okay.
Yeah. Good. All right, so that was the direct map cache. Typically, because of the issues of conflict misses, most processors do not have direct map caches. They have set associative caches of some level of associativity. So we'll take the simplest level of associativity that's not direct map. Suppose we have 2 lines per set. Okay, then again we use the bits here. There'll be little s bits here to find a particular set. And now that leaves, in this case, 2 things we want to check. And we just do, there's logic to do a parallel comparison against all the tags. And in this case, the 2 tags. And wherever there's a hit, and if the valid bit is set, then we know we have our data. And then we use, again, our block offset to figure out where the data starts in that cache line. Okay. And so if this is and then the type of the value retrieved indicates the sort of the other end of it, right? So in green we show that if you were just doing a 2-byte operation, then that's what you would access. And as before, if either the valid bit is not set or there's no match among all the sets, then we have a miss. And the only difference here is now we have a choice. Okay, we can choose to put the new thing here or here. Okay, and that's what defines the replacement policy. Most frequent one is our sort of variance of least recently used, which says that if I look at these 2 things and I see one has been accessed more recently, this is the more recent one, right? If I just got done touching this, earlier than the last time I touched that, then maybe this has kind of gone stale. I'm not going to need this one anymore, so I'll get rid of this one and keep the others. All right, so how might your code look? So let's say that, again, so now we have equals 2. Keep it simple, we'll just have s equals 2. We're sticking to b equals 2, which means we have 1 bit for the offset, 1 bit for the index, and since, okay, didn't write it here, but since there's 4-bit addresses, we're assuming as before, that leaves only 2 bits left for the tag. Okay, and they're color coded here. So now it's the exact same address sequence. Oh, good.
So how would you decide how many bits to give to the tag? Do you just need enough so that you can identify the key elements that you have in each set?
So typically what's done is you don't want any false positive, false negative. So you want to make sure that the tag is unique, right? So every single address in the virtual address in the system will use these same, discard these same bits and have the rest of these bits as tag, okay? And all the ones that match in these bits here will either go to different sets or different places within the set, okay? So this tag uniquely defines a location. Therefore, it's a unique comparison. There are certainly other settings besides processors in which the tag bits, sometimes called the fingerprint of what you're looking up, is reduced, greatly reduced to be something more like one that you suggested, that it's just large enough that you're very unlikely to have a collision, and so you can distinguish things that are the same versus things that are different. In this case, we don't want to have any probability of that kind of collision, and so we just use all the rest of the address as the tag. Okay, so again, the things are color-coded. So we have the exact same sequence as before, but this time, so it starts off the same. We get this initial miss, and now we have a choice of where in the set to place it. Let's say we place it in the first position here. And then we have a hit as before because it goes exactly here again. Then we get a miss. Okay, we're a completely different set. So let's go ahead and place it there. Then another miss. Okay, but here it's in set 0. The tag is 1, 0. We don't have a tag of 1, 0 together with a valid bit anywhere here. So it's still a miss, but there's space for it without having to evict anything. Okay, so we get this in the cache as before, but we didn't have to evict this earlier one, which gives us the win we're looking for, because now this has gone from a miss to a hit. Okay. Any questions on that? Yes?
So, one thing that I guess I noticed that in each case you're accessing essentially 1 byte. Is there like you're only trying to get 1 byte? When reading more than 1 byte, is it possible for that read as directed from the trace to span multiple lines?
So the original address, this is similar to the earlier question, right? The original address can, of course, span multiple cache lines. Like maybe you're telling it that you want to fetch this stuff here, and the cache boundary is right here. That will get translated into 2 cache line requests and a shift and so forth, because you're gonna, let's say you want to bring that into a register, right? So you get this piece from one cache line, you get this piece from another cache line, you have to shift over this first piece and then put the other one in the lower bytes of the register. And so you can see it's rather more expensive, right, all around. And so therefore, if either the cache, if either the compiler can move this so this is aligned, right? If it's like an array, maybe add some padding so things are aligned, or otherwise try to make things aligned, then it's much more efficient. Okay, good. Okay, so that was all about reads. So the issue with writes is that you're changing the data. So you've got these cache copies in the memory hierarchy, and now you're changing them, right? So particularly changing the L1 would be the first one that got changed. So if it's a hit to the cache, then there's basically two policies, write through and write back. So write through says that you update the value in the cache and you update the value in the next level of the cache and so forth, all the way down throughout the cache hierarchy. As you can imagine, that's rather costly to do right away, because oftentimes you're writing things, because of locality, you're writing things multiple times before they get evicted, say, from the cache. So a much more common policy is write back, and that is that you let the other levels of the hierarchy be stale. They hold the old values, and the system has to make sure that the right things, proper things happen. One of the things it needs to do is it needs to keep track of which things have changed. And so for that, we add an additional bit besides the valid bit called the dirty bit. Okay, and that's initially 0 for a read, but it's 1 for a write, either when you bring it in or anytime subsequent something's in the cache, you write it, you go ahead and set the dirty bit. Okay, what that tells the system is that if you go to evict this, right, it's the victim in a replacement policy, then if this bit is 0, then what I know is the next level of the cache hierarchy has the same value, and so it's up to date, and I can just drop this on the floor. On the other hand, if this is a 1, that says that this cache line has the most recent value. What's in the other levels of the cache, the memory hierarchy, are stale, and so therefore I need to update. When I evict this, I need to update the copy of it in the next level of the hierarchy in the system. Okay, so if this is, for instance, the L1, and I do an eviction for the L1, then the L2 I need to update. If it's in the L2, I need to update the value there and declare it and mark it as dirty, so it's all up to date, right? So therefore, the next time maybe it gets fetched from the L2, then it will have the proper value. If on the other hand it gets evicted from the L2, then the same thing happens on down the hierarchy. Yes?
That was my question.
Okay. Okay. So on a write miss, we have a couple of choices. One is that we can do an allocate, which basically, you load in the cache and update the line in the cache. The other is that you write straight to the memory and you don't put it into the cache. Okay, and so these kind of go hand in hand. If you're doing a write through, there's no necessarily reason to load it into the cache. If you're doing a write back, then clearly the cache is the freshest copy of the data, and so you need to allocate a place for it in the cache. Okay. All right, and again, this is by far the most common. All right, so I said that these lookups are done based on the different bit combinations in the address, and so having the lowest order bits be for the placement inside the cache line makes perfect sense, right? Because all the upper level bits, because once you have a cache line, then because bits are laid out, memory is laid out consecutive in memory, then all the bytes from 000 up to 111 will just be consecutive in memory, okay? And so therefore, if you truncate these, this to be the exact size of a cache line, that means that all these things will be consecutive in the cache line, okay? So that's why you want to use these bits to do the lookup within the cache line. But what about these bits? I mean, this is just does a lookup to pick a set, okay? It's at first blush maybe seems arbitrary that you pick these low order bits, and maybe even problematic in some settings, right? Maybe some bits scatter across things, or maybe the high order bits or whatever would be good. So for instance, let's look at an alternative way of method, which would be high bit indexing, right? Suppose we took the S highest order bits as the index set. What might happen? Okay, so let's use this illustration. So this is memory. We have a direct map cache, keeping it simple. There are 4 sets, okay? And we'll just show color-coded where the sets fall in memory. So if we have middle bit indexing, they look like this, okay? Basically, if you go across the sets, if this is like one big array and you were just scanning through the array, you would cycle through the sets, right? Green, yellow, blue, pink, blue, and so forth, okay? And so that would make it more likely that you were using your cache, spreading the data across your cache, okay? And so therefore, less likely to have conflict misses. On the other hand, with the high order bits, it's the other extreme, in which you basically take in your address space and divide it into 4 consecutive partitions. So if you allocated an array that, for instance, was only this big, then all the access to that array would hit to the same set, okay? And that would be very poor use of your cache. Okay. So that just gives you a little bit of hint as to why things are done the way they are. Any questions on that? Okay, so as I mentioned in the Intel Core i7 processors, like the one we looked at before, there's registers. There's an L1 for data and an L1 for instructions, an L2. Then there's an L3 that we saw in that die that gets shared among all the cores, and main memory. And here are some typical sizes: 32 kilobytes for each of the instruction data caches, 8-way set associative. 256, so not all that much larger for the L2, much larger for the L3, a little bit higher, even higher associativity. Cache line sizes are 64 bytes throughout the system. And you can see something about the latency. So an L1 hit is 4 cycles, and L2 is roughly 10. L3s can be 40 to 75 cycles, depending on how close the memory bank is to where your core is, and so forth. Okay. Okay. So let's look at drill down a little bit more on that. So let's suppose that we use some realistic numbers instead of the toy numbers we've used before. So we have a 32 kilobyte 8-way set associative L1 data cache. Again, the cache line size are 64, so this is our B equals 64. Right, 8-way set associative, so that's our S, right? Okay. All right. So again, this is our cheat sheet here, and the tag and X. Okay. So all right. So I already said that B was 64, right? S is 8. What about E? How big is E? Well, you have to work backwards, right? So we said that the B was 64, so that's 6 bits for the tag for the block offset, right? 2 to the 6 is 64. There are S is 8. Right, so that means there are, but 3 bits, no, sorry, 8, wait, so, sorry, this is E, I got this backwards. You guys should stop me when I make stupid mistakes.
That's not, I was gonna stop you.
Sorry, good. You need to look around more, okay. This is E, all right, there we go, much better. Okay, so this is 8, which makes this 3. Okay, so good. So now, all right. So how big's the tag? Well, the tag is going to be, so this is 6, and this is the, let's see, the tag, 47-bit address range. Okay, so we want the total number of this to be 47, right? And so how many sets do we end up with? So, anybody know here? I'm getting myself in a hole here. 3. Did that work out? 3, 9. Bit address range. All right, well, let me just cheat since I'm getting myself out there. Okay. All right, so the total of this was 47. Good. The tag ends up being 35. The block offset, as we said, was 6 bits for that and 6 bits for that. Okay. 5, 6, 12, 47. Okay, that is 47. Okay, good. Okay. Okay, here's what I was overlooking. Did you ever see what I was overlooking? They gave us the capacity of the cache. That was the missing piece, okay? So once I know this thing is 32 kilobytes, okay, then I know that the product of S times E times B has got to be 32 kilobytes. Okay, so that's here. All right, good. So from that, I was supposed to be able to work backwards and say, okay, so if I know that I have my B and I have my E, so I have 3 knowns and 1 unknown, and that's how I derive 64. Okay, so from the 64, I get the 6, and then from the 47, I get the 35. Okay, so that was my mistake. I wasn't looking at the size of the cache as the missing variable to figure this out. Okay, so again, as long as you're given 3 of the 4 numbers you need, you can figure out what what all these things are. Okay, question is that? Okay, so given that that's the case, we know that we have 6 bits. So let's look at this address. This is in hex. So we look at the low order bits, and we split it up into the S bits and the B bits. There's 6 of each. And so what we see is that the tag here is all zeros. So we get, the tag is set, and this is all zeros. So we get a 0 here. The block offset is this here, which is 1, 0 in hex. Or 16, and the tag is all the rest of the stuff. Okay. Okay, so it's the 35 bits that are left from there. Okay. Yes.
How did you know that the block offset is 6 bits?
Because the cache line size is 64 bytes. So we were given that B was 64, and you take the log of that. Okay, other questions? Yes?
Shouldn't set index be between tiny block offset of that, but where does that go?
Yeah, so this was the block offset here. This was the set index here. And the rest of the bits were tagged. So what's a little confusing is you have to translate from the hex down to the binary, right? So this is 0 hex, 1 hex, 0. It looks like binary, but it's really hex. Okay, other questions on that? Okay, so we talk about the miss rate for a cache. That's the rate at which the fraction memory references where you go to look for it in the cache and you don't find it there. So typical numbers are, for L1, it's between 3 and 10%. For L2, it can be even smaller. The hit time is, again, if you miss, you have to go to the next level of the cache. And how long does it take to fetch things from that? If you miss all the way out to main memory, then compared to the, say, 4 and 10 cycle hit times for L1 and L2, it's up to 200 cycles for main memory, and that gap is increasing. So therefore, there's this huge difference between a hit and a miss, which is, for instance, 100x almost for L1 and main memory. And so this is kind of an interesting way to think about it. So if I tell you I'm getting 99% hits, and in one case and 97% hits in another case, you might think, oh, well, that's pretty similar. All right, we're ballpark. But actually, 99% hits is twice as fast as 97% hits, right? And this is illustrated by a simplified example. If I have a cache hit time of 1 cycle and a miss penalty of 100 cycles, then if 97% of the time, if 97% hits, that means 3% of the time I pay this expensive thing. And so when you multiply that and add it up, you get 4 cycles. With 99%, I only get this expensive thing once, 1% of the time, and so it's only 2 cycles. Okay, so the average access time is double when the hit rate drops from 99% to 97%. Okay, and this is why, because of that sort of false sense of goodness, that we talk about the miss rates as the hit rates, because the miss rates, of course, will focus exactly on the fact that these numbers are different, dramatically different, right? Factor 3 off. Okay, so to write cache-friendly code, you want to, if your code want to make the stuff you're doing frequently cache-friendly. So inner loops is a good place to always look. You want to minimize the misses in inner loops. We've shown a bunch of techniques for doing that. Repeated references to variables are good, particularly if they're in registers, right? Then that's really fast. Don't go out to memory at all. And then stride 1 reference patterns are good, right? Because then you hit in the cache if you're touching items in the same cache line. Cache lines are 64 bytes long, so you can read, for instance, 8 consecutive doubles, and they're all hits after the first one. Okay, and so our qualitative notion of locality is quantified through things like analyzing miss rates, which are a function of the organization of the cache and the size of the cache. Okay, questions on that? All right, so let's do the quiz. All right, let's see how people are doing. Ah, okay. Interesting. Okay, so the first question was review. Again, we're about to do a midterm for you all, so it's good to try to remember this stuff. Yeah, basically the float. The float is 4 bytes, and then you have this array of characters, which is 5 bytes. Okay, but then the whole thing has to be a multiple of the largest item, which is 4 bytes. So it has to be a multiple of 4 bytes, and the next largest multiple of 4 above 9 is 12. Okay. Okay, this one. All right, what do we have here? So we have, we need bits for the offset. So the offset is 8, so you need 3 bits for that. We need bits for the set index. The set, so there's 4, so we need 2 bits for that. And so with a 16-bit address, that leaves 16 minus 5, 11 bits left. Questions on that? Okay, so this is the correct answer here. And most people got, I mean, it was the favorite. It's the favorite answer. All right. And what is the total capacity? The total capacity is just the product of these things. So you have, if you have 4 sets, and each set has 2 lines in it, and each line is 8 bytes. And, sorry, it has 4. What did I do wrong here? So if each line has 2 bytes, there are 4 sets. No, that's 64. Okay, good. So my math's messed up. All right, so that's how you get 64. Okay, and people got that one right. All right, 700. Good. Questions on the quiz? Okay, good. Okay, so let's talk about performance impact of caches. So the cover of your book shows a picture of a memory mountain. And Randy covered this in the first day of class, remind you of that, but this is how it's generated. So what it's showing is read throughput, the bandwidth you're able to get, the number of bytes read from memory per second as across different settings. And the memory mountain shows this read throughput as a function of things that capture spatial locality and temporal locality. So here's what the code looks like. You have this big array of data, and you every time you call test, you pass it 2 arguments, elms and stride. You call test once to warm up the caches, and then you call it again to measure the throughput. And if you see what happens is this is uses that loop unrolling trick we showed before, that you do 4 accesses within each inner loop. And so that would be starting from I to I plus the stride times 2, I plus the stride times 3. Okay, so that'll get you sort of 4 consecutive accesses according to whatever integer you set for stride. So if the stride of 1, this is just get you I plus 1, I plus 2, I plus 3. But if the stride is 4, this gets you I plus 4, I plus 8, I plus 12. All right, and you do that until you're done, and then there's if there's some rounding error in terms of things dividing evenly, there's this last little bit, but most of the throughput overwhelmingly is from there, and then you return the sum of those 4 accumulations. Okay. All right. So here's what you get for the features of the Haswell Core i7 processor. Again, it has the memory hierarchy characteristics that we've been discussing. And what you can see from here is that on this axis, we're varying the stride. So here's stride 1, that's the best case, and then it gets higher and higher. And over here, we're varying the size of the data that we're cycling through, right? So remember, we have this warm-up, so we run through the whole data to warm up the cache, and then we start measuring the throughput. So if the data, after warming up, it fits inside the cache entirely, then we'll get all hits from there on, okay? And that's kind of what happens up here, all right? Because the size of the cache, again, is 32 kilobytes, so if that's the size of the thing we're cycling through, we're getting the highest throughput, right? So here, up is good. Okay, so what you can observe from here is these ridges, which correspond to the different cache sizes. So L1, this ridge up here, when your data fits within the L1 cache, then you get this nice ridge performance here. As soon as you no longer fit in the cache, then you get a lot of capacity misses, and but those get serviced in the L2 cache, which is 256K, so somewhere in here. Okay, you get all those. And then if you're too big for that, then you get serviced in the L3 cache. So this is sort of up to 8 megabytes, where this drops off again, and then the rest is in memory. Okay? And the way the stride impacts things is it's sort of the spatial locality, right? That basically stride 1 always has the best spatial locality. Stride 2, you're sort of you kind of you only use half the cache, half the cache line, and so twice as fast. You're getting twice. The number of misses increases by factor 2, and so forth. Okay, and this are all the stride. You multiply that by 8 bytes. So this 11 stride of 11 times 8 bytes, or 88 bytes. Okay, any questions on this picture? All right, now you can understand your book cover. We're only how many weeks into the course, and you now know the cover of the book. All right. Okay. So how can you help things out in your programs? Well, one thing you can do, similar to what we showed before in the previous class, is you can rearrange the loops. Okay. So if we have matrix multiplication, then we've got these 2 n by n matrices that we're multiplying, A and B. We're putting the result in C. We're accumulating into a sum that starts at 0, and then the Cij element is the sum over all these k's of A k times k j. Okay, and so then you write back the answer here. And so sum will typically be held in a register. And so let's see how that does. Well, again, so we're going to assume that this n, so remember we had this special case last class where we said, if n is really small, then you can actually get locality more than just the inner loop. But that's not the typical case, so we're going to consider the typical case where this n is very large. And so by the time you get kind of the second time through the innermost loop, you've already blown out the cache. Okay, so you can't even hold multiple rows in the cache. All right, so if that happens, and that's a fairly common setting, then how can we analyze the cache? So remember we said there's a row major order. So each row is contiguous in memory. So if we want to step through the columns one row, then it's this last index that we step through. And so as long as the block size is bigger than the size of a data item, in other words, as long as you can fit more than one data item in a cache line, then this is a very nice access pattern. And in fact, you only miss every time you have to bring in a new cache line. So for instance, if you could fit 8 data items in a cache line, then you do 1 miss and then 7 hits. So your miss rate is 1 out of 8. Okay, that's all this is saying here. It's 1 out of over 8. All right. But on the other hand, if you step through the rows in one column, then you're jumping in huge strides way past the end of the cache in memory, and so there's certainly no spatial locality. And so you get a miss rate of 100%. Okay, so what does this look like? If we look at the A loop, this is the index that's changing, so we are going row-wise in A. And so, if a block size is 32, so it holds 4 doubles, then it's 1 over 4, or the miss rate is 0.25 in that case. B, we're accessing the wrong direction, so it's a 1, and C is just basically sitting in the register, so it's, this item of C in this inner loop is no cache misses whatsoever. Okay? So what if we do if we rearrange the loops? Okay? Well, there's some rearranging that's not going to matter much when n is this much bigger than the cache size. So, for instance, in the supplemental slides, we show the case where these two are swapped, but k is still kept as the innermost loop, and the miss rates are identical. And you can look at the supplemental slides for that. So let's try something more interesting. Let's try k not being in the inner loop. So if we make k the outer loop, then what happens is that J is the inner loop, and so B is now accessed in a good way. C is now accessed in a good way, and A is now the one that's basically when the inner loop is fixed. And so you get very different characteristics and better numbers, right? Because you have a 25, 0.25, 0.25 and a 0, as opposed to a 1, 0.25 and a 0. If we were to put I in the innermost loop, and similar, if we swap these two, the supplemental slides show it's the exact same miss rate. So the only other pair of combinations are where I is the innermost loop, and we either do JK or KJ. The analysis is the same. This is disaster because A is column-wise, C is column-wise, and so you're getting 100% miss rates on both of these. Questions on that? So either the compiler or you as a programmer should keep that in mind and look at your innermost loops and make sure that you're getting the best behavior you can. All right, good. And this is just summarizing again the misses per iteration. This is the best case. How does it play out in reality? So this is experiments run, and it shows again that this is log scale. Okay, so this is much worse. So cycles per. So this is good. We're happy down here, right? We're unhappy up there, and we can see that the ones, as the theory predicted, the ones where J is the innermost loop are excellent, and the K ones are much worse, and the I ones are even worse. Okay, so that's rearranging loops. Let me just spend 2 minutes talking about blocking. So you can get further locality in matrix multiplication by not just rearranging the inner loops, but also doing things blocks at a time. Let me just go ahead and skip to pictures like this, where you're pulling entire blocks, which consists of little square matrices of multiple rows and columns, one by one, by having an entire set of innermost loops triply nested innermost loops to go with your triply nested outermost loops that you had before. And if you do that, then you can go through the analysis and show that the number of misses drops significantly. The constraint you have is that you want, at any time you're working on one of these blocks, you're working on 3 of them at a time, and you want all 3 to fit inside in your cache size at once, so they don't thrash each other, right? So as long as you can fit all of them in there, you're good. This B here is not the B from our cache parameters. This is the B, which is sort of the dimension of the block, right? Block size here is B times B. So subject to this constraint, the locality improves with larger and larger B. So you want to push B as big as you can while keeping it, the whole thing, 3 times B squared fitting in cache. And the total misses ends up being divided by something that grows as B, which you didn't have that B term before. Right, so here's the comparison. In the no blocking case, when we did the analysis and over the entire run of the program, you had n cubed times 9/8 misses. But in the blocking case, you still have an n cubed term, but it's multiplied by this expression here, which is much better. Right? So as B grows, that gets much better than the non-blocking case. And that's why all practical matrix multiplication codes do blocking. Okay. So in summary, cache memories can have significant performance impact, and you want to write your programs to make good use of the cache by understanding how data is laid out, understanding the properties of the cache, and